All right, today's starter is about RC circuits. Okay, let's say we have a 120 volt source, and then we have a 100 ohm resistor and a 0.48 farad capacitor. So that's a pretty big capacitor. And at t equals 0, the switch is closed. And we want to know what is the current at t equals 20 seconds. And what is the magnetic field at point A, which is right here, which is half a millimeter from this wire right here. And one of the things I said was that you can ignore the rest of the circuit. Just treat this like a long straight wire, and we'll just call the magnetic field due to the other wires negligible. And so let's solve. Well, this is an RC circuit, and so what I kind of do I kind of construct the equation myself so that because I have a hard time memorizing things. So we want the current as a function of time. This is for part A. And, well, I know it's e to the negative t over RC. I know it involves that. And the thing is that if I have this situation going, I know that current is a function of time, that it's going to start off at its maximum. When I close the switch, there's no charge built up on the capacitor yet, so there's no voltage drop across the capacitor. So all the voltage drop has to be across this resistor. So it's going to start off at its maximum current, and then as the capacitor fills, the current will gradually go to 0 with this exponential function. So what I want is I want this to be 1 at t equals 0. And I know that we have E equals IR, so I'm going to have the maximum. So this is just going to be E over R. I don't need the 1 minus E to the negative t over RC. That's the other version of it, because it's starting off here. So at t equals 0, you have e to the 0 power, which is 1. You have e to the e over r current. So that's that's how I figure out what that is. Okay, so I need to solve for t here. Or I'm sorry, I need to just solve for the current. That's right. So all I need to do is plug in my values. It's already solved for it. So E is 120 volts. R is 100 ohms. And this is e to the negative 20 seconds over and 100 times 48 farads is 48 seconds. And so I just need to plug all that into my calculator. So where's my E button? Okay, so we've got 20. Come on, turn it on. 20 divided by 48 equals, let's make that negative 1. So negative 0.41666, so on. And then where is, there it is. So I'm going to, on my calculator, I go second. Having calculator issues here. Times 120 divided by 100. And I got 0.791. Is that what you guys got? Okay. 0.7 791 amps. So that's the current in that wire. Now, what is the magnetic field at a point which is 0.5 millimeters from the wire? And we're just going to treat this like a long straight wire. So the magnetic field for a long straight wire is mu naught I over 2 pi times r. R is the distance from the wire to here. So this is 4 pi times 10 to the negative 7. And this is going to be Tesla meters per amp times, well, we know what the current is. And then we have a 2 pi, and then 1 millimeter is 0.0005 or point meters. Did I do that right? Okay. So let's see if I got the units right here. Meters, meters, amps, amps. Left with Teslas. By the way, that's kind of enough. The way I memorize what the units are for mu naught, I remember, I don't know, I have memorized 4 pi times 10 to the negative 7, but the units, I just use this. Well, I got to cancel out the amps, and I got to cancel out the meters down here. So I just kind of reconstruct the units for mu naught by looking at the equation. That's not a good way to check to see if you did your work right, but that's what I did. Okay, so 4 times pi times 10 to the negative 7 times 0.791 divided by, oh, I should have just canceled out, oh well, 2 divided by pi divided by 0.0005, and I got 3.16 times 10 to the negative 4 Teslas. Is that what you guys got? Okay. Okay. All right. Now let me show you something here. Let's extend this problem a little bit. What if I just looked at this wire, from, let's start from here over to here and just stretch it out over here. Let's make it really long wire. So, and we said, okay, right here, here's a little place that's close to this wire, and we said that the magnetic field half a millimeter away from the wire was this. But, so, and we have Amperes Law, which says that if you go B dot ds equals mu naught I enclosed. Well, if I drew a little Amperian loop, around, well, let's pick some distance out here. Let's put my point A right here, just to make it bigger. Well, it's pretty obvious what current I have enclosed here. We figured it out. It's 0.791 at 20 seconds anyway. So that's the current enclosed. What if I drew my loop right here around the capacitor? What's the current enclosed by this loop? There isn't any, right? There's no current across that capacitor. So, I mean, there's no current across the capacitor, but, so, if I drew a cross-sectional area, there's no current through the loop. So you'd say, well, no current through the loop means mu naught I enclosed is 0, which means we shouldn't measure any the magnetic field should be 0. But guess what? Right here and right here, we measure exactly the same amount of magnetic field. When we do the experiment, the capacitor has no effect on that. What's going on? Okay, well, that's the mystery we're going to solve next. That is all.